It is the third part of section 5.3, Tucker conditions and complementary slackness. The KKT approach is a generalization of the method of Lagrange multipliers. The KKT method allows inequality constraints, while the Lagrange multiply method deals with only equality constraints. First, recall the linear support vector machine formulated in this objective function as minimization over W and W0 of half W norm squared subject to this inequality constraint defined on each I from 1 to n. N is the number of data points. Now, we define is Lagrangian to original object function. Now, here, along with the Lagrange multiplier, we sum the left-hand side of the constraint and subtract. Okay, that is Lagrangian. And we call alpha I and dual variable or Lagrange multiplier. Okay, the original problem can be equivalently formulated in this primal problem. So mean over W and max alpha of the Lagrangian subject to alpha non-negative. That is dual feasibility. We'll try to get alpha non-negative. And its dual problem can be formed by changing minimum and maximum, max alpha and mean over W of the Lagrangian. That is dual problem. Now we first try to minimize that portion by using calculus techniques. Differentiate it and equate to 0, then we can get some necessary conditions. Okay, so those conditions are called KKT conditions, and also called first order necessary conditions. It's a sort of a first derivative test. Okay, we'll see here the conditions. W derivative, so the gradient of W, gradient W with respect to W and Lagrangian is this one, equal 0 implies this equation. Now W0 derivative is this one, equal 0, and we have another equation. Now alpha I is non-negative, that is dual feasibility. And the last one is the primal feasibility. And the primal problem requires these constraints. Okay, now that one, and this portion times alpha I equal 0, that is called complementary slackness. This slackness will make the problem much simpler, and now solution will be much effective. Later on, I'll explain what it is on page 111. Okay, now let's see the Lagrangian. This is the original Lagrangian. Okay, we defined the Lagrangian in this way, but now sigma can be applied here term by term. Then that term will be alpha I yi W0, and the next term will be alpha I W transpose xi, and last term will be here minus minus, so that plus alpha I summation. So that is exactly the original Lagrangian. Now we'll use the conditions here. Okay, W0 is independent of I, so we can put outside here. Then the remainder part is 0. Okay. Now here W transport is independent of I, so we can put out. Then now remainder part is W, so that this whole thing is the same as W transpose W. So we have here. Now we can combine these two to get this one. Now yet the Lagrangian is not a function of alpha, but also is a function of W. So we have to replace this term so that eventually the Lagrangian must be a function of alpha. Okay. By using the first KKT condition, and W norm squared is same as W dot W. So here we have minus half W norm squared is same as minus half W dot W. These summations can be written in this double summation, and we have that. Now this term will be replaced by that one, and we reach at the dual problem. Okay, that minus half norm squared is replaced by that one. And this is a dual problem, and to be maximized over alpha with the constraint alpha I non-negative, and that is the second KKT condition here. Right? So we have to solve it. And it can be solved by using quadratic programming solver, or we may use sequential minimal optimization algorithm. At the end of the section, we'll deal with the algorithm in detail. So at this moment, we'll assume that we solve that. And we have alpha star, the maximizer, the vector. We assume we solve that. Then, once we assume that is solved, then by using the first condition, here alpha I is decided, then W star can be decided. So here we have W star. Now remainder part is W0 star. Okay, before considering how to get this one, we look at the objective function here. Now this one is involving xi, xj dot product. So this whole thing is a linear combination of xi, xj dot product. Now when we need to expand the linear subject machine for nonlinear algorithm, we'll try to replace this portion to become nonlinear function of xi and xj. Later we'll do that. Okay, let's go to now here how to get W0 star. Okay, again here we momentarily assume we have that, and we consider the complementary Slackness condition. Now we have this one, and out of that we can get that. Now we assume that value is already obtained. Then the complementary Slackness is this equation. Alpha I is positive. Then this part must be 0. So that is now 1. Now, but alpha I cannot be negative because the dual feasibility does not allow alpha I negative. Right? It must be non-negative. Okay. Now, once it is positive, this portion is positive, then alpha I must be 0. and it cannot be negative because this is from the primal feasibility. Okay, here we define optimal scoring function. That is basically here net input, optimal net input for given xi. Now we have W star and W0 star, so that is now optimal net input for that one. Here this one says that here along with yi multiplication there is 1. Now that one is saying that once is larger than 1, then here alpha is 0. Okay, let me explain what it is. In the beginning, when we introduce the supported vector machine, we start with here the data set of two classes. One is points of O, marked with O, and then the other class is marked with here the plots, right? And support vector machine is trying to find the maximum margin. Okay, that is the O. Okay, now maximum margin, so that we are trying to get boundary and around here, and then try to maximize the margin. And this line, this boundary is basically here, and f star at xi is the same as 1. That one is f star at xi equal -1, right? And along with yi multiplication, this is 1 and that is 1. Now, in alpha I is positive, then now the corresponding xr is on the boundary. Okay, 1 means that 1 or -1 means here xi must be on the boundary. Now, that is positive means that the points here not on the boundary, far away, for that one, the corresponding the dual variable is 0, so that only alpha I here non-positive is around here the vectors. For instance, this point and that point, now alpha I is not 0. Except that every else alpha will be 0. Such points are called supported vectors. Okay, and now along with some other select variables, now these points are nearest to the boundary. However, for this original linear supported vector machine, in fact, these points are on the boundary. Okay, so only non-zero, only positive alpha appears on the boundary. Every else alpha will be 0. Okay, now here, and anyway, we know that once W0 is decided, then always it must be here along with yi, this value must be larger than or equal to 1. And here, if we have, so that eventually there is at least one point on each boundary such that the minimum of this value will be 1. So that is a supported vector. So that we write down this one, and here, so that we consider now only this is a positive 1, and now we apply minimum over there, so that W0 star is same as 1 minus minimum this value under the condition yr equal 1. So we can get W0 star by using this formula. And after defining some vector and matrices, we'll summarize the support vector machine later on. But here, the thing is, in the beginning, we assumed we get alpha. Once alpha is decided, then we can get W star, the optimal W, and then also we can get the W0 star, right? Okay, here I'll explain what the complementary slackness is. Okay, there are 3 types of constraints. And the first one is binding constraint. That is one where some optimal solution is on the hyperplane for the constraint. Okay, if you consider, for example, linear programming, then it's easy to understand. And each constraint will make here line segment, and now, okay, in fact, lines like that. Okay, each one will lines, and the inequality will make one side, so that once you are considering linear programming, then along with this 5 constraint, now the feasible region is decided. And linear programming, the solution will be on a vertex. So assume solution is here. Then these 2 are binding constraint. And now binding constraint and non-binding constraint is no optimal solution is on the line for the constraint, so that the other 3 are non-binding constraint. And redundant constraint is 1, so that even though it is eliminated, the feasible region is not changed. Probably there is another constraint so that it is now one line is made, but that one is not changing the here the feasible region. So in this case, the corresponding constraint for this line must be a redundant constraint. There are only 3 types of constraint. Here we have complementary slackness theorem. Assume the primary problem P has solution W star, and the dual problem has solution alpha star. Once the primary variable in jth variable is positive, then now jth constraint in dual, that is primal variable, and is positive, then here jth constraint in dual is binding, which means that among the inequality, equality is satisfied. Now, and alpha I star is positive, that means that the dual variable is positive, then the ith component, then ith constraint in primal is binding. That means again here now inequality turns to be equality for ith component. Okay. So the complementary slackness refers to a relationship between the slackness in the primal constraint and the slackness of the associate dual variable in primal constraint and dual variable. Okay, and you have to notice that the number of variables in the dual is the same as the number of constraints in the primal. And in our case, right now, the number of variables in dual is in fact alpha I. So alpha I is from 1 to n. that one in primal problem, in fact, inequality is made for each data point, so that there are n data points, so that there are n constraints in the primal. You can easily check that, and the number of constraints in the dual is equal to the number of variables in the primal. Okay, so usually we say that a constraint has slack if it is not binding. So for this second sentence, we consider a contrapositive statement. Here, if it is not true, then not that one. Okay, so here, if ith constraint in P is not binding, then alpha star is 0. Okay, or equivalently, you can say that if the ith constraint in primal has slack, then alpha equals 0. That is exactly the same statement as this one is not binding, so that equality only inequality, so not equal, so it's not binding, then now that is 0, right? Alpha star is 0. Okay, so that is exactly representing the equation. Okay. Okay, this is about the complementary slackness. Okay, we'll continue in the fourth part of the section. Thank you.